Hello and welcome back to Let's Code Physics. This is episode 2 in our series on the Drude model of circuits. We are taking the Drude model of electron behavior and trying to create a circuit simulation out of it. Last time we were successfully able to get an electron to move under the influence of an electric field while being scattered off of randomized collisions, representing mostly the atoms in the material. We're not going to worry currently about the collision between electrons. Speaking of electrons, plural, the goal of today's video is to implement multiple electrons in our code. In order to accomplish that, I've created a new class called Electrons. So I'm trying to expand my knowledge of object-oriented programming, so I am creating my own class here. The electron, as it's currently defined, needs to be given a position by the user. So when you call this class down, or when you create an object of this class down below, you've got to give it its position. We want a visual representation, so we are storing in the electron.particle a sphere. Again, it's going to be green because that's the color electrons were in my high school chemistry textbook. We give it its position. We give it a relatively small radius, so it's not taking up a huge segment of the screen. We'll turn on this make trail a little bit later. This allows you to see the path that each electron has taken. Here we're giving the electron speed like we had before. So this is the speed that the electron reverts to whenever it encounters a scattering event. So whenever it runs into another particle, this is the speed that it'll spit back out with. We've also got its initial velocity here. It's going a little bit to the right, just to give it some motion at the beginning. I could make this 0. It'll accelerate under the electric field, so it doesn't matter too much. And then we've got the scattering time. So again, this is a measure of how densely packed the material is. And last episode, I got myself confused at the end. I took this in one direction, thinking I was taking it in another. So the larger you make this, the more free the electron is of scattering events. The smaller you make it, then the more scattering events the electron is going to encounter per second. So increasing this is a decrease in the material's resistivity. Decreasing this is an increase in the material's resistivity. Sometimes in physics we prefer to work with the conductivity, which is a measure of how well the material conducts electric current. So increasing this increases its conductivity, and decreasing scattering time decreases the material's conductivity. Another thing I did, since now we're going to be updating the position of many electrons, I decided to move the position update to a separate subroutine. So we're going to be calling this down later with this move electrons. And basically it's looping over all the electrons that we store in the electron list. There's going to be 30 of those in today's simulation. And it just runs through the same process that we had before. It evaluates whether there's a scattering event. If there is, then it randomly reassigns the electron's velocity with the given speed above, that's this self.speed here, at a randomized angle. And again, we're not going to be moving in the z direction, we're just going to do this in 2 dimensions. We could do it in 3 dimensions, but then I would need 2 angles. I'd need a planar angle and a polar angle. If there's not a scattering event, then we just update the velocity in the usual way of force times dt. And then either way, we update the position. Now I'm adding in one additional calculation here, which is this average position. So this is allowing us to keep track of where the electrons are. So for each update, we are going to calculate the average location of each electron, its x component, y component, z component of its position vector. And then it'll return that vector so that we can graph its components later. So down here is where we create our set of electrons. There's going to be 30 of them. We're keeping track of them in this electron list. And for right now, we're going to start them all out at the same location. That's not physically reasonable. You know, we would expect them to be randomly distributed or uniformly distributed across the sample. But just for the sake of seeing how this scattering event impacts our electron behavior, I wanted to have them all start at the same location. So they've all got the same initial condition, and any differences in their path is the result of the difference in their scattering events up here. And like before, we've got our electric field. It's going to be pointing in the x direction, so we should see movement in the x direction overall, and basically the y direction should average out to 0. And then down here we've got our while loop, so this is going to be running to update the position here in Move Electrons. And then we'll also here graph the average x-coordinate, y-coordinate, and z-coordinate of each of our 30 lovely electrons that are going to be bouncing around this material. So now that we've taken a look at the code, let's run it. So there are the electrons. You see there was this giant blob of electron at the beginning. So they all started at the same location, but they've quickly flown apart from each other because of the randomized scattering events. You do notice that they're tending to be on the right side of the screen. They also seem to be getting smaller because, like we saw last time, the viewport is zooming out as the electrons move to the right. If we take a look at our graph here, the green represents the average x position or x coordinate of these electrons. You notice that that is pretty steadily increasing. It's behaving a little bit better than it did last time because now we're averaging over 30 electrons. The y component has been positive for the most part. That happened the last time I ran this. I'm not sure why that is, or if it is oscillating about 0 with a very long period. And then of course the z component in blue is a flat 0 because we're not exerting any force or creating any velocity in the z direction. In fact, I could even rotate this view this way, so now you're looking at it along the y-axis. So now the z-axis is going this way, and so they're all flattened into this plane. So we've got a 2D material, which is pretty cool. So we're dealing with graphene or stannine or silicene. We've now got those are the three that I know of. These three two-dimensional materials. Like last time, we're expecting this to become a relatively consistent line because of the scattering. We end up with Ohm's law instead of an acceleration. So instead of a quadratic graph, we've got a linear graph here. And let's repeat our little experiment from last time of trying to get the average velocity off of this thing. Here's my calculator. Okay, so let's pick a point here. So at 1,000, we've gone about 40. I'm just doing a rough calculation here. So 40 divided by 1,000. Okay, so that gives us an average speed of 0.04. So I'm calling that the current in finger quotation marks, just because to get the actual current, we'd have to do some calculations on that. But it would be proportional to this. So it's the current apart from some multiplication or division by some constant factors. So what I could do then would be to double the electric field, for example, and we saw last time that should double the speed of these things. So that should double the slope of this line. It certainly looks like our electrons are more active. Okay, and this time my y velocity is heading down in the y direction. Okay, in the negative direction. So actually, I stopped paying attention to it once this thing got, upwards more. Let's see. So if I take a point on here, I've got 225 over 20. Let's run that. 225 over 20 gives me a much higher average speed. That's interesting. I thought that was supposed to double. I took the wrong way. I need to take 20 over 225. There we go. Always be suspicious when things jump up an order of magnitude. Okay, yeah, so we went from 0.04 to 0.08, or 0.09, and this was Yeah, and with some rounding, that's basically double. Cool. That's nice, and that's a nice visualization of the velocity, but you know, I'm having to do a calculation to get the velocity out of it. It would be nice if I could get the code to calculate the velocity for me. And then I look over here and I see, oh, it is calculating the velocity for me. How nice of you, code. So what I can do is I can, instead of calculating the average position, I can calculate the average velocity. We'll do it the same initialization here. So we'll initialize it to 0 because we need to be adding to that. Only now, instead of calculating, I guess I can still calculate average position. Average velocity. Oh, I need to actually add it up here. Excuse me. So we'll calculate our average velocity up here. So we just add on each particle's velocity. And then we'll divide that by the number of electrons so that it's an average. I mean, you know, either way, that's, you know, we're just dividing by a constant. And now instead of returning average position, I'd like it to return average velocity. And so down here, we'll call this average velocity. I could just call it average position, but then I'll get confused later when my position curve looks flat. And then we'll change these folks as well. Comment those out. There we go. And I just use Control-Alt-3, pretty handy shortcut in the idle editor. Cool. So now it should give me a basically flat curve with the velocity. Sphere has no attribute velocity. Oh, that's right. That's right. The I don't need particle there. I need just e.vel because the position is assigned to the sphere, but the velocity is assigned to the electron itself. There we go. Excuse me, velocity. I called it vel there to match pos there, but it's spelled out as velocity. Right there, 3 lines above. All right. One more time. I prepare these codes ahead of time to avoid moments like that, Brian. Okay. So what we've got here is pretty wide variation. So that is not showing up nice and flat like I want it to. Okay, so I was making things way more complicated than I needed to, trying to calculate the average velocity. What I really need to do is just calculate the average velocity, the change in position divided by the change in time. Since I'm starting at 0, 0, 0, it doesn't matter that I've got just the position here, and then I can just divide that by the time over here since I'm starting my time at 0. Let's run that and take a look. Oh, right, I cannot have my t start at 0. I need to have it start at dt. Actually, I suppose... Oh, no, wait, I can have it start at 0 if I just move this increment up to here. There we go. And that makes more sense because I'm taking care of all my updates, then I'm taking care of my graphs. Okay, we're going to graph this thing now. Okay, cool. So you notice that the red, for example, the Y component shows its oscillation like it did before. But now we're getting a steadier 0 down there. So we're averaging now over all the electrons, and we're averaging over time. And that's the thing that I had to cut to figure out how to do, and ultimately came down to the simpler solution. Again, here you notice it's oscillating at first, but then it levels out to our right around our value that we had before, our 0.08 almost. There it's just above 0.08. So the longer you let this run, the more smooth this will become, the flatter it'll be. Let's try let's try doubling the electric field again. Again, that should result in about a doubling of the average velocity, since that's pretty much the current in the Drude model in Ohm's law. And there we've got a 0.18, so a little more than 2 times, well, of course we had a little more than 0.08 last time, so that worked out well. Good. Okay, one more thing I'd like to do. I promised you we would do this. I would like us to turn on the make trail. This is probably going to make it run slower because it's having to animate more things. But what this is going to do, this is going to leave a path behind each electron as they travel around this material. Now remember, the electrons all start in the same location, so this will give us an idea of what the scattering behavior looks like. And there you get an idea of the randomness of it. We do have a cluster kind of within here, and you notice all their trails, they are moving toward the right, so they kind of all started here, and their paths are kind of growing out this way. And of course the scattering events are randomized, so these paths should be different if I restart the program, because they're getting scattered at different points and at different angles. So for example, we didn't have this guy shooting off last time. That just took one slightly different scattering event to get him up this way. We had another one symmetrically going down this way. So that's kind of cool. You could use a system like this to, you could zoom in and turn that into, a coloring book page or something. That would be fun. So this is what electron trails look like in a material. Obviously, they're not going to start at the same location. In fact, why don't we, to finish this out, let's change these to some randomized ones. This will be the last thing we do for today. So we'll do x equals uniform, and let's have it start anywhere from -1 to 1. So that's the initial viewport of the screen. And then we'll do the same thing with y. And that's setting them to two different random variables. Let's see what we get from this. Okay, yeah, so they all start randomly. So basically the initial starting location is broadened out. And so we end up with these going out this way. I'm not sure what happened with our y velocity there. That's rather bizarre. Oh, because it's taking the average position. Right, I need to... so I actually need to adjust that speed calculation based on that. Okay, well, that was fun for the sake of that being uniform. I suppose what I could do is make a list of initial positions. And then what I can do is I can say init underscore position dot append vector x comma y comma 0. And then all I have to do to get the average speed is take average position dot x. Oh, what I actually... okay. What I actually want then is... let's see. Oh, what I can do is I can make this thing a... I know, I said the animation would be the last thing I did, and then I got distracted. Let's make this thing a global variable, init position. Cool. And now what I can do is I can have the average position be the eParticle.pos minus init underscore position. Oh, but then I need to be able to reference... Okay, all right. I need to do this a little bit differently here, because I need to be able to reference the electron on there. So what I should actually do is just store that under electron. Let's see. So let's have self.init underscore position equals vector. All right, I don't even need to do that. I can just do position. There we go. Okay, and now what I can do is I can, instead of worrying about that, I can say e.initial position. So now this average position is really the average displacement. Really average displacement. There we go. So now I can just take that there. I don't need to worry about this anymore. Oh, invalid syntax. Oh, I started an extra... Oh, I added an extra paren here. Yeah, there we go. That's better. Okay, cool. Yeah, those are better behaved now. So now I can have them start at random locations, and I can still calculate the average velocity. That's pretty awesome. And that should be... Yeah, that's the same it was last time. Okay, cool. So in the last couple minutes of this video, I broke my code and then fixed it. So I think that's a good stopping point. Next time, we'll start putting these electrons into a wire. So instead of having them be able to, wander all the way around the infinitely large viewport here, we'll give them boundaries that they have to bounce off of, and we'll see what that does in terms of Ohm's law. next time. Bye-bye.